Hello everyone, we'll discuss the basics of perceptrons. So we have studied linear models like linear regression, logistic regression. Basically the inputs are always features like x1, x2 and so on up to xn. Okay, then we find coefficients for those inputs, basically coefficients for x1, x2 up to xn, and that forms the model for us. So normally we call it as a1 x1 plus a2 x2 plus so on up to an xn, but here we can interpret them as weights. Okay, weights are nothing but coefficients. You can think of them as coefficients. Okay, so those are w1, w2 up to wn. So these are the weights or the coefficients of the features x1, x2 up to xn. Okay, so effectively your model or the output y, okay, your output y is nothing but w1 x1 plus w2 x2 plus up to so on plus wn xn, and pictorially we can represent it as, so this is the x1, this is x2 and so on up to, so we have this input layer up to xn. Okay, and basically we want to multiply x1 with w1. This is how it is denoted pictorially. We want to multiply x2 with w2 and we want to multiply xn with wn. Okay, and all of these are added together. Okay, and that gives us the output, which is y. So these are all inputs, input features, and this is the output. So this is the pictorial representation of a linear model. Okay, now you can also think of it as a neuron. Okay, so basically if the output is 1, if the output is 1, it is said that it is equivalent to a neuron firing in the brain. Basically neurons, they form a chain. Okay, so one neuron connects to another neuron through synapses. Okay, and they transfer electrical signals, etc. Okay, so this is like the head of the neuron. These are all the inputs that it gets, and if the inputs are potent enough to trigger the output, then it triggers or fires the neuron. You can think of it that way. Now how is the neuron fired, or when is the output 1? When, okay, this is true when the product, basically, okay, when the product of the summation, basically sum of the products, so summation of wi xi, I goes from 1 to n. Okay, basically I goes from 1 to n. This is greater than the threshold. This is greater than the threshold. Now what we want to do is, because see, you are familiar with the linear model very much, you are very familiar, you are very well acquainted, you know the linear model very well, right? You know linear regression very well, you know logistic regression very well. So we still want to include the threshold, but we still want to frame it as if it's still something, it should still look like a familiar linear model. Okay, so right now what we are saying is, if basically summation I goes from 1 to n, wi xi exceeds threshold, then we want to say that basically the neuron will be fired, that is output y will be equal to 1, else y will be equal to 0 if it is less than or equal to the threshold. Okay, now we want to introduce the threshold in an interesting way by using the concept of a bias. Okay, we want to introduce a bias. So if you remember, in a linear model we always have a bias. So if you remember any linear model, we used to have something like y is equal to wx plus b, where b used to be the bias term, or y equal to mx plus c, the intercept term, right? So that bias, keeping up with the weight terminology, we want that bias to be w0. And what is the coefficient of that bias? If I frame it as, let's say, w0 instead of b, the coefficient is 1 right now. So I am creating this additional neuron, which is not an actual input, but it's bias term. Okay. Now, what we can say is, if W naught is the bias, then in order to keep the equation looking like, or in order to make sure that the equation still looks like the familiar linear model, we will say that the threshold is minus W naught. Okay, if bias is W naught, then the threshold will be minus W naught. Okay, and so we'll say that if summation I goes from 1 to n, wi xi plus, if it is greater than minus W naught, then y will be equal to 1. Fair enough? Now, let's say, okay, so what I'm saying is w1 x1 plus w2 x2 plus up to so on plus wn xn is greater than w0, minus w0. Why minus w0? Because if I bring it back on the left hand side, then it will look like w0 plus w1 x1 plus w2 x2 plus wn xn is greater than 0, right? Okay, then y is equal to 1, else y is equal to 0. Okay, so this is easier for us to understand. That's why we introduce a bias term, because if we don't have a bias term, we'll always have to make sure that our linear model, or the line that separates the classes, has to always pass through the origin, which is not true in general case. Okay, so now because of this bias term, now our linear separator, or linear separator between the two classes, the official term is the hyperplane or the margin. Basically margin. Okay, this is the official term or official name for it. Can pass, or you can say need not mandatorily pass through the origin. Okay, we can adjust the bias term so that our model can be adjusted, it can be more flexible. Okay, now in order to bring the right hand side into summation w multiplied by x form, we have a w term over here, but we don't have an x term. Okay, so we'll introduce an x naught, which is always equal to 1, and we'll say this is w naught x naught plus w1 x1 plus w2 x2 plus up to so on plus wn xn is greater than 0, then y is equal to 1. Okay, and of course we can put it in summation properly and all. Now the output can only be 0 or 1, right? So if output is greater than threshold, okay, so right now what we have done is, the threshold was minus w naught, we took it on the left hand side, and then we added an x naught term to it and all. So now we can say that if this entire term is greater than 0, then the output should be 1. Now the same thing we can write in equation form, okay, and we can use a step function which is denoted by A. So A is basically an activation function, what activates my perceptron, or what activates or fires the neuron, what causes the output, activation function, but mathematically it's only a step function. It's only a step function. So basically, if a of z is equal to 0, if z is a negative number or 0, and a of z is equal to 1 if z is greater than 0. Okay, so if I apply activation function, then what I can say is my output, that is y as a function of x, is actually applying a, the activation function, to w0 x0 plus w1 x1 plus so on plus wn xn. Okay, and this entire term I can call as z. So let z be equal to summation I goes from 0 to n wi xi. So then I can say that it is simply my output y, the function of x, which is basically applying activation function to z. Okay, so, or I can also write it as a dot product of two vectors. Imagine that we have two vectors. Okay, let the vector w, or simply bold w vector, be equal to w0 w1 up to wn, and x vector, the input vector, or bold x, be equal to x0 x1 up to xn. Okay, so then if I simply take the dot product of w dot x dot product, this is nothing but z, so I can say that the output y is applying activation function to the dot product of w and x. Okay, so this is the basic of a perceptron. Now for example, if I give you a simple perceptron, let's say one input is +1, another input is also +1, third input is -1, here the weight is -0.1, here the weight is 0.4, and here the weight is -0.4. So what will be the answer? What will be the output if this is given to this particular thing? What will be the output? Okay, so y is equal to applying activation function to the dot product of w and x. So here what is w? The weights are -0.1, 0.4 and -0.4, and they are multiplied by x1, x2 and x3. Okay, here we are not considering any bias. Okay, this is a given example. Okay, so if there is no bias, if it passes through the origin, there is no bias. Okay, so in this case it is -0.1 into 1 plus 0.4 into 1 plus -0.4 into -1. Okay, so if you calculate this, this will come out to be this 0.4 will be 0.8, -1 is -0.1 is 0.7. Because 0.7 is greater than 0, the output will be 1. So these were the basics of the perceptron.